Topics covered in this video collection are: what is an inverted V amateur radio antenna? What is a folded dipole antenna? Yagi-Uda antenna. What is a half-wave dipole antenna? What is a delta loop antenna? What is a multiband HF fan dipole antenna? What is a ground plane vertical antenna in amateur radio? What is Moxon antenna or Moxon rectangle in amateur radio? What is a half-wave slope antenna in amateur radio? What is standing wave ratio SWR? Balanced and unbalanced transmission lines in amateur radio. What is a Balun in amateur radio? Can you use TV coaxial cable for amateur radio? What is a dummy load in amateur radio? What is an antenna tuner in amateur radio? Inverted V antenna is very popular among radio amateurs, especially the beginners, as it is very easy to put up and has a fairly good performance. As the name implies, it has an inverted V appearance, with the two limbs of the antenna forming an inverted V, with the apex at the tip of the non-conducting mast. As the horizontal dimension is lesser than that of a horizontal half-wave dipole antenna, it is useful when there are space constraints. Though theoretically the performance of a horizontal dipole and inverted V are similar, practically it can be lower for the inverted V. This is because of proximity to the ground, effect of ground conductivity, and end effects. Elevating the antenna higher above the ground can improve the performance of the inverted V, though it may not always be possible in a given location. In a folded dipole antenna, a half wavelength conductor is folded into a longitudinal loop and fed at the center. It has a higher impedance of around 280 ohms compared to the 70 ohms impedance of a horizontal half-wave dipole antenna. Hence, while a coaxial cable is suited for a horizontal half-wave dipole antenna, a twin-lead transmission line with about 300 ohms impedance is used for a folded half-wave dipole antenna. Half-wave folded dipole is commonly used as the driven element of a Yagi multi-element antenna. Like a half-wave dipole antenna, the folded dipole is also resonant and radiates well at odd integer multiples of half wavelengths. As mentioned in case of half-wave dipole antenna, it acts as a 3/2 wavelength dipole at 3 times the fundamental frequency. Folded half-wave dipole antenna is preferred when the impedance has to be higher. Yagi-Uda antenna is often called just a Yagi antenna. It was invented in 1926 and consisted of a driven element, a reflector behind the driven element, and directors in front of the driven element. In case of amateur radio, ham radio, the driven element is connected to the transceiver. Yagi antenna was a common sight on rooftops of houses earlier when they were used to receive television stations before cable and satellite TV became popular. Reflector and directors are called parasitic elements. Reflector is usually 5% longer than the driven element, while directors are shorter. Yagi antenna has a much higher gain and directivity than a simple dipole antenna. Gain is usually about 10 dB. Gain increases as the number of directors increase in a decremental fashion. Reflector can give a gain of about 5 dB, while directors can add 1 dB and lesser. The interlinking rod is called as boom. Half-wave dipole antenna fed at the center is the commonest type of dipole antenna, and its length is almost half of the wavelength of the frequency for which it is meant. So, the total length of a half-wave dipole antenna for the 40-meter amateur radio band will be almost 20 meter. The space needed for the antenna increases as you go down along the amateur radio bands. I had the opportunity to use both 40-meter and 80-meter half-wave dipole antenna earlier, but I'll have to struggle to get even a 20-meter half-wave dipole antenna up at my current location. Maximum radiation from the half-wave dipole is perpendicular to the conductor with almost zero radiation along the axis of the conductor. This would also mean that it would act as an omnidirectional antenna if installed in a vertical position. But installing half-wave dipole in a vertical position would not be easy for a lower amateur band. In my earlier days of ham radio, I used to simply tie the half-wave dipole across two tall coconut trees using plastic twisted flex threads. Threads would be tied to stones and flung up on top of palm leaves and pulled up in a pulley-like fashion. Of course, those half-wave dipoles used to sag in the center due to the weight of the connecting coaxial cable, and it would be almost a V antenna. A half-wave dipole antenna can also be used at odd multiples of its fundamental resonant frequency. Thus, a 40-meter or 7 MHz half-wave dipole can be used for 21 MHz but not for 14 MHz. It will act as a 3x2 wave dipole antenna at 21 MHz. The directional gain of a half-wave dipole antenna at the resonant frequency is about 2 dB. Delta loop antenna is a full wavelength antenna in the shape of the Greek alphabet delta. The antenna forms a delta shape with limbs like an equilateral triangle. Though it can be made with base at the top, bottom or sides, practically it will be easy to have the base at the top as shown in the picture below. It will need a 4:1 Balun at the feed point for impedance matching. Otherwise, the SWR, standing wave ratio, will be high. As with the half-wave dipole antenna, a delta loop antenna for 7 MHz will also function well with the odd multiple frequency of 21 MHz. On 14 MHz, the antenna impedance is high and SWR will be high. For the center of 7 MHz amateur radio band with frequency of 7.1 MHz, the length of the delta loop will be 43.14 meter. Delta loop antenna is fairly easy to construct if you can put up two strong poles. Recommended height is above 18.3 meters for a 40-meter antenna, which comes down to 4.6 meter for a 15-meter delta loop. Fan dipole uses a group of parallel dipoles for different amateur radio bands fed from the same feeder coaxial cable so that the elements fan out from the feed point to either side. Impedance of each dipole is low at its resonant frequency and high at other frequencies. So a 40-meter dipole does not absorb much power at 20 meter. Each element to either side will have a length corresponding to the quarter wavelength of that frequency. Fan dipole can be mounted as a horizontal dipole or in an inverted V configuration if there is space constraints. The different elements should not correspond to odd multiple frequencies like 7 MHz and 21 MHz. In that case, both will have low impedance at 21 MHz. The elements of different bands need not be parallel but will need additional anchors in that case. Parallel elements do not need additional anchors but need insulators to keep them spaced. Dipoles are balanced while coaxial feeder is not. Hence, a balun is needed at the feed point to prevent the outer conductor of the coax from radiating RF power. Ground plane vertical antenna is often used for VHF transmission in amateur radio. The vertical portion of the antenna is quarter wavelength. Usually, the ground plane is formed by 4 equally spaced radials of quarter wavelength each. Central conductor of the coaxial cable is connected to the vertical element and the metallic sleeve of the coax is connected to the radials which form the ground plane. Another option is to have a conducting ground plane of at least quarter wavelength in radius. This can be considered for a mobile antenna mounted on top of a metallic vehicle body. It is an omnidirectional antenna which radiates equally in all directions. Feed point impedance is usually half that of a dipole, about 36 ohms. SWR will be less than 2:1 when connected with a 50 ohms coaxial cable. Moxon antenna, also known as Moxon rectangle, is a two-element single-frequency antenna named after Le Moxon. It is similar to a two-element Yagi-Uda antenna with folded dipole elements and no directors. Slightly less than half of the rectangle is the driven element, which radiates the power. The other part, which is slightly more than half, acts as the reflector. It has modest directivity with a high front-to-back ratio. The driven element is mechanically connected to the parasitic element or reflector with an insulator. Moxon software from AC6LA can be used to calculate the dimensions of the Moxon rectangle antenna. Elements could be made of wire or aluminum tubings. The antenna is mounted with the rectangle horizontal and has gain in the direction of the feed point. If the elements are of wire, additional supports will be needed. Half-wave sloper antenna is also known simply as sloper antenna. It is useful when there is only a single vertical support and limited horizontal space, which is common in city dwellings. Typically, the slope may be 45 to 60 degrees. Lower end of the wire has to be at least 1/6 of the wavelength above the electrical ground. Sloper has a low angle radiation pattern suitable for DX communications. The outer sleeve of the coax will pick up RF radiated from the antenna and cause RF interference in equipments like computers in the Radio Shack. This can be prevented by winding a part of the feeder coax just before entering the shack into an RF choke. 8 turns of the coax wound on a 4-inch PVC former will serve as an RF choke, preventing the entry of signals picked up by the coax sleeve into the shack. Going through the QASET.com pages of many amateur radio operators, I came across EFHW or end-fed half-wave antenna often. Unlike the center-fed half-wave dipole antenna, feed point is at a high voltage point of the radiating element instead of at the high current point. While the center-fed half-wave dipole resonates at odd multiples of half wavelength, EFHW operates at odd and even multiples of a half wavelength. This would mean a truly multi-band operation for the radio amateur. But EFHW has high feed point impedance of around 5000 ohms, unlike the 72 ohms of the center-fed half-wave dipole, which matches easily with the 50 ohms coaxial cable. This necessitates the use of a matching transformer for EFHW. This matching transformer is called UNUN as it matches an unbalanced antenna to an unbalanced feed line. A small counterpoise is used beyond the feed point. As the EFHW is a single wire, it is easy to set up, especially for portable operation. Standing wave occurs when there is impedance mismatch between the transmission line and the load, which is the antenna. When there is an impedance mismatch, part of the signal is reflected back to the transmitter. This reduces the effective power transmitted and thereby the efficiency. Standing wave can be considered as a resultant of forward and reflected waves together. Standing wave ratio or SWR is the ratio between the maximum and minimum amplitudes of the standing wave. Highest level of SWR occurs when the antenna is not connected, open circuit, or when there is short circuit in the transmission line. SWR can be in terms of voltage, known as voltage SWR, and current, known as current SWR. Usually, it is the voltage SWR that is measured using an SWR meter. Ideal SWR is 1 and high SWR above 2 can cause heating of the transmission line and final power amplifier of the transmitter circuit and likely to cause severe damage. Typical example of a balanced line is a ladder line, which is often used to connect to a center-fed sub-antenna for multi-band operation. It has 2 parallel conductors spaced by insulators. Air acts as the dielectric between the conductors. Spacers at 12-inch intervals could be of ceramic or fiberglass. Impedance of the line may vary from 300 ohms to 600 ohms. Impedance is calculated using the formula Z is equal to 276 into log 2s by d ohms, where Z is the feeder line impedance, S is the center-to-center distance between the conductor wires, and d the diameter of the conductors. The dimensions are in inches. In case of a balanced line, neither conductor is connected to the ground. A matching tuner circuit is used between the 50 ohms transmitter and the 300 to 600 ohms ladder line. Typical unbalanced line is a coaxial cable which has one central core separated from the other conducting sleeve by an insulator like plastic or Teflon. The sleeve is grounded at the transmitter. Current in the center conductor and that on the inside of the shield of the coaxial cable are equal but opposite. Due to skin effect, another current flows on the outside of the shield from the connection point of the shield and antenna back to the connector on the transmitter and hence to the ground. This third current depends on the length of the transmission line. If the line length is an integral multiple of half wavelength, it has a low input impedance and permits the flow of current. This can be prevented by the use of a Balun or balanced to unbalanced transformer. Balun provides a fixed ratio of impedance transformation and limits the flow of unbalanced current flowing on the outside of the shield. Information courtesy ARRL website. Balun stands for balanced line to unbalanced line. It is typically connected between a balanced antenna and an unbalanced feeder coaxial cable. Balun is a type of transformer. A 1:1 Balun will connect to a 50 ohms unbalanced line and present a balanced output at 50 ohms. Often a 4:1 Balun is there in an antenna tuner to convert the feeder line impedance to a range which the tuner can handle. In the yesteryears, a common use of Balun was at the television end of the feeder line from the external antenna to match feeder impedance to that of the television set. There are current balance and voltage balance, of which current balance are typically used in antenna connections. Balun can take the form of a classical transformer with primary and secondary windings, or an auto transformer with a single tapped winding. Another option is to use an RF choke as a Balun. This can be done by coiling a few turns of the coax at the antenna feed point. Coax can be wound on a ferrite toroid to act as an RF choke. Aim is to prevent the RF from traveling along the outer sleeve conductor of the coax. TV coaxial cable typically has a characteristic impedance of 75 ohms, while the output impedance of an amateur radio is 50 ohms. So if you use a TV cable for amateur radio, there will be feeder losses. Ideal would be to use a cable like RG213 with characteristic impedance of 50 ohms. As a disclaimer, I was using TV cable for my solid state VU2 VW and QRP and 3x807 hybrid QRO, both homebrew. But at that time, I did not have access to RG213. Moreover, as a rule, vacuum tubes were more tolerant to mismatches than the current day solid state devices. Though I never had my 807s going QRT, I had lost many BD137s which were used as final for the solid state QRP. I kept on replacing them and sometimes even cooling them with a small aluminum dish with ice kept over the BD139 as a homebrew heatsink. When I bought a VHF base station later, I could get RG213 cables. That VHF base station is working even today after 25 years, even though it has some snags, obviously, as it was kept idle for the past 10 years. Dummy load is a device connected to the output of an amateur radio transmitter for testing purpose. Electrically, it simulates an antenna and allows adjustment of the transmitter without sending out electromagnetic waves. It can also be called as a dummy antenna. Using a transmitter without a dummy load or antenna leads to reflection of power back to the final stages, causing overheating and damage to the circuitry. Typically, a dummy load consists of a resistor with value equivalent to the output impedance of the transmitter and the characteristic impedance of the antenna, usually 50 ohms. As the resistor can heat up when the power is delivered, a cooling system is needed. A simple method is to immerse it in mineral oil, which absorbs the heat generated. Dummy loads with other types of heat sinks are also commercially available. Dummy load provides an SWR of 1:1 to avoid power being reflected back to the transmitter. If you adjust the transmitter by connecting the antenna instead, it will cause interference on the amateur radio band. Antenna tuner is a device used to match the output impedance of the transceiver to that of the antenna. Optimal transfer of power occurs when the antenna is tuned to the frequency with a low standing wave ratio or SWR. When the antenna is mismatched, there will be high SWR leading to low radiated power and heating up of the final RF power amplifier as well as the feeder coax. It is always better to have good matching of the impedances without the antenna tuner, and antenna tuner being used to adjust minor mismatches. My friend used to tell that with an antenna tuner, one could even load the signal to a window grill, but the radiated power will be low. This also occurs when one tries to use a 14 MHz antenna for 7 MHz or vice versa. You can use a 7 MHz half-wave dipole for 21 MHz, which is an odd multiple harmonic frequency. Most of the current day transceivers are built for an output impedance of 50 ohms. Many of them also have a built-in automatic antenna tuner. They also have automatic power output reduction mechanisms to reduce power in case of mismatch to avoid damage to the RF power amplifier. Antenna tuner circuits of handheld VHF-UHF transceivers have to work only on a narrow range of frequencies, unlike the HF, which needs to work on a high range of frequencies. An SWR meter is useful along with antenna tuner to look for mismatch and adjust the tuning in case of mismatch for HF transceivers. More detailed information can be provided by antenna analyzers or impedance bridges. A remote antenna tuner attached to the antenna will be more efficient than one attached to the transceiver, but technically more difficult to implement.